Today, we're talking about digital manufacturing, where we can literally turn code into physical objects. But what happens when someone secretly corrupts that code? What if they could create an invisible flaw that could cause a drone to fall out of the sky or a critical medical implant to fail? So the way 3D printing basically works is pretty straightforward. You start with a digital blueprint, right? A CAD file. That file then gets sliced up into a whole bunch of layers and turned into a set of instructions called G-code. Now, G-code is the language the printer actually understands. It tells the machine exactly where to move, how fast to go, and when to spit out material. It's really the final set of commands before a digital idea becomes a real thing. But here's where the problem is, that G-code, it's just a text file. And because it's just text, it can be changed. Someone could get in there and slip in these tiny, almost impossible to see errors into the instructions. The printer, well, it'll just do what it's told, and it'll produce a part that looks totally perfect to the naked eye, but inside it's fatally weak. You can imagine a sabotaged airplane part or a faulty surgical guide. The stakes are incredibly high. So to figure out how to defend against this kind of invisible sabotage, a group of researchers did something really clever. They turned the whole thing into a game, a head-to-head contest between attackers and defenders. It was a classic red team versus blue team setup. The red team's job was to be the bad guys. Their goal was to secretly mess with a few of these G-code files to make the final parts weaker. The blue team, they were the defenders. Their job was to find those compromised files. It's basically a high-tech game of cat and mouse. Now, here's the really crucial part, the handicap they gave the blue team. They had to find the sabotaged files, which was a real needle in a haystack problem, without getting to see the original perfect design file. So they couldn't just do a simple comparison between a suspicious file and a golden copy. Nope. They had to find the flaws using nothing but the G-code file itself. They were flying blind. Okay, so what kind of tricks did the red team have up their sleeves? Let's take a look at their playbook. The main strategy was just brilliantly simple. In G-code, the command G1 basically means move to a new spot and squeeze out material while you're going. But the command G0 means move to a new spot but don't squeeze out any material. So the attackers just found a few of those G1 commands and sneakily changed them to G0. The printer head still moves along the exact same path, so everything looks right, but for a tiny little stretch, it's not laying down any plastic. And that creates a tiny invisible gap, a void, inside the part. And here you can actually see what that looks like. On the left, that's the path for a perfect part. On the right, that's the sabotaged version. And if you look really, really closely, you can see those tiny little gaps where the printer head moved but didn't actually deposit any material. It's a microscopic change in the code that creates a huge structural problem, but you would never ever see it just by looking at the finished part. The red team didn't just have one trick, though. They actually used 6 different kinds of attacks to see what the defenders could catch. Some were like we just saw, converting commands. Others just deleted them entirely. And I want you to pay attention to attack ID 3. That one's particularly sneaky. It reduces the amount of material everywhere, all at once, by a flat 50%. Remember that one. It's going to be important later. All right, so the traps are set. Now, how did the blue team, the digital detectives, try to find these hidden flaws? Okay, so the blue team's whole theory rested on this one big idea, that any change, no matter how tiny, would leave behind some kind of statistical fingerprint. They figured if the attackers were changing or deleting commands, then the total number of those commands in a bad file should look weird when you compare it to a normal one. And you know what? At first, this super simple idea works like a charm. For the first smaller dataset of about 180 files, the blue team literally just counted the commands in each file and threw them on a graph. And look at that. 2 files, marked here in red, immediately jumped out. They had way fewer commands than all their neighbors. It was a perfect catch. But when they got to the much larger dataset with over 4,000 files, just counting one thing at a time wasn't going to cut it. So they had to get a little smarter. This graph here shows what they did. They started plotting 2 things at once. The number of G1 extrude commands, those are the blue dots, against the number of G0 move commands, the orange crosses. This let them spot files that had a really suspicious ratio of commands. Their other main strategy was to bring in the big guns, machine learning. The idea here was to let an AI look at all the different stats for all the files at once and automatically group or cluster the ones that looked similar to each other. Any files that the AI couldn't fit into a normal-looking group would get flagged as a weirdo, an outlier.
So this is basically what the AI saw when it looked at that huge second data set. Each little dot here is a single file. You can see these two massive groups, the big blue one and the big orange one. Those are all the normal files. But what about all those other little scattered groups of color? Well, those are the outliers. Those are the files the AI pointed to and said, hey, something's weird over here. It's like an automated system for finding that needle in the haystack.
So after all the attacks from the red team and the high-tech investigation from the blue team, what was the final score? Who actually won this thing? Well, this table really tells the whole story. The clear winner was the human-guided combined statistical analysis. It managed to find 50 of the 60 hidden attacks. And, this is critical, it had 0 false alarms. It never cried wolf. The machine learning methods, they did okay, but look at the false positives. One of them flagged almost 200 clean files as suspicious. In the real world, that's a huge problem. But hang on a second. The best method? It still missed 10 attacks. And in fact, every single defense method missed these exact same 10 files. That means there was one type of attack that was for all intents and purposes completely invisible. The ghost in the machine was attack ID 3. Remember that one? This was the attack that didn't just change a few commands in one little spot. Instead, it reduced the amount of extruded material by exactly 50% across every single line of the code. And that's exactly why it was so devious. Because the change was applied globally and uniformly, it didn't create a weird statistical spike, it didn't look like an outlier, the file didn't seem broken at all. It just looked like a different but totally valid and internally consistent G-code file. It blended in perfectly, fooling both the human-led checks and the AI. The final part would be printed 50% weaker than it should be, and absolutely no one would know, until it was too late. So I think the big takeaway here is that even as we get smarter and smarter about finding digital sabotage, the attackers are getting smarter right along with us. And this whole experiment leaves us with a really deep and kind of unsettling question for our modern world. When the line between a line of code and a physical object gets this blurry, how can we ever be 100% sure that the things we build are actually what we think they are?